Hi, in this video we're gonna tackle elasticity, but I'm gonna give you very basic revision of elasticity here. So if you are not familiar or you just forgot a lot of information about elasticity, just click the link that you can find in the description of this video, and then you will find more basic information about elasticity. Okay, so elasticity of y with respect to x is simply defined as percentage change in y divided by percentage change in x. What do we mean by these percentage changes here? That we will have delta y over y divided by delta x over x. Now, if I multiply it all out, I will get that this is delta y over delta x divided by y over x. And this is like general expression for elasticity that you've been using in microeconomics. But during introduction to economic analysis, we were also discussing point elasticity. Again, if you're not familiar, please click the link in the description below. You will find all the information on the subject. So, what we did when we wanted to find point elasticity, we replaced those two with these, which meant we were talking about tiny changes, and consequently the formula for elasticity that we've obtained took the form involving derivative. And look, we basically said that here we have marginal function divided by average function. Okay, now what about the interpretation? Let's just say that I calculated this elasticity and I got z. How do I interpret it? If x increases by 1%, then z changes. Then y changes by z percent. Remember, this is important. This is a ratio of percentage changes. So z actually translates 1% change in x to z to some percentage change in y. And look, I written here increases by 1%, but here changes. Well, it changes. Well, because this can be either positive or negative. You see, elasticity of supply will be positive, elasticity of demand will be negative. Okay, now, I think this is enough repetition, but what we're going to do today is that we're going to learn a new way of calculating elasticity that has actually tremendous applications in both economics and statistics. Okay, and look, we will use logarithms for it. But before we derive the formula, let me make some initial assumptions. Okay, let's just say that u is simply ln x. So we have 3 bars, we define u to be ln x. Then the function that interests us is simply y equals some ln x. And then we have something maybe looking a little bit weird to you, but we will have e to the power, so simply x, the same x as you got here, is defined as e to the power of ln x, right? To which power I need to take e in order to get x? I get this power, so this is equal to x. And let's just say that I'm going to define also that this is equal to ev. It will make just the calculations simple. Okay, so what I'm going to do now is I'm going to calculate derivative of ln y with respect to ln x. So, what am I getting? So, in other words, I can write it as du d dv, right? Now, I can multiply this by 1. For example, my 1 will be dy divided by dy, and the second one, dx, divided by dx. Look, those cancel each other out, those cancel each other out. This must be true. Okay, and now let's write what are we getting. First, over here. So, du dy. Okay, u is equal to, oh my god, I'm sorry. It should be ln y over here, of course. It should be ln y from the beginning. My bad, sorry. So, dy, so derivative of u with respect to derivative of u with respect to y is simply 1 over y. Okay, here we have dy dx. We don't want to get rid of this. This is the part we like. And now dv dx. Look, dv dx is this function. So this is the function x, right? So if I differentiate this with respect to v, I can just get ev. But we should remember that ev is also equal to x. And now, if I reorganize this expression a little bit, what am I getting? Marginal function divided by average function, elasticity of y with respect to x. And look, this is how we obtain the new way of calculating elasticity. We simply need to logarithmize function in order to obtain it. Okay, let me illustrate this to you with a couple of simple examples. Okay, example number 1. Let's just say the demand function is given by quantity is equal to k divided by p. So some k divided by price level. And look, it makes perfect sense. The bigger the p, by bigger number we divide k, the lower the q. This works as demand function perfect. Okay, so what is the easiest way to find price elasticity of demand? Well, of course, first we logarithmize it. Oh, I'm sorry. Of course, minus. Now, does this look familiar? Look, we can treat, if I assume that this is y, this is b, and this is minus x. Look, this is a simple linear function, but with logarithms, right? So now, look, if I want to find derivative to find elasticity when we are using natural logarithms, but also you should notice that this function has constant elasticity. Look, elasticity does not depend on which part of the function we are. And look, this actually leads us to two very interesting conclusions. First, if I'm going to graph this function is going to look like this. If I put price here and quantity here, just like we did in Introduction to Economic Analysis, this function looks like this, right? And we know that it has constant elasticity equal to -1 at each point of this function. Okay, now, but what does this imply to us? Let's figure out, as you did before probably in microeconomics, what is the relationship here between elasticity, generally between this function and total revenue? And look, total revenue is price times quantity, right? So now, if I substitute this for quantity, I get this is price times K over price equals to K. So look, actually, it doesn't matter at which point we choose. If we choose this price, some P0, we will be able to sell Q0 units. So look, this thing is P times Q. This is total revenue, right? Let's call it total revenue 0. If I'm going to choose some price P1, this area, we will have quantity Q1. This is total revenue 1. But as it turns out, both of those are equal, and they are both equal to K. But of course, remember that this is the fact that we have constant elasticity function is not sufficient for this to happen. Actually, you need to have elasticity equal to -1 for this to happen. Let me just show you this. Imagine that we have the same problem, but now we've got p to the power of n, right? So if I logarithmize both sides, I get that this is ln q equals ln k minus n ln p. Again, elasticity of price elasticity of demand is equal to derivative of ln q with respect to derivative of ln p, which gives us -n. Right? So we will also have constant elasticity in this demand function. But look, now if I'm going to calculate total revenue, I'm going to have that this is price times k p to the power of n, which gives us k times p to the power 1 minus n. And in this case, total revenue is not always constant, but in this particular case, it is. Okay, so now let's try another example. This time we are going to broaden our horizon a little bit because we're going to move from generally elasticity to partial elasticity. And look, first thing we're going to do is production function. So combine this production function. So we've got k to the power of alpha, L to the power of beta. So we've got level of production in a country is equal to level of capital to the power alpha, level of labor to the power beta. Now, what is the capital elasticity of income. Now, in order to answer this question, again, we need to logarithmize the function. We've got that this is ln y equals to alpha ln k plus beta ln l. And look, in this case, elasticity of income with respect to capital, which is the partial, remember, partial derivative. But what do we mean by partial? Assuming labor stays constant, right? So, assuming labor stays constant, if we increase capital by 1%, then level of GDP increases by alpha percent. And by the same token, elasticity of income with respect to labor is beta. If we increase labor by 1% while keeping capital constant, level of income increases by beta percent. Okay. I don't think that was very much complicated, so let's just do one more model. This model is called gravity model of trade. Okay, so look, gravity model of trade is a model that is very empirical and it's really easy to estimate econometrically. Actually, if you want to see how to estimate a model like this that I'm going to show, click to the second link in the description of the video. You will see how to get data and how to estimate a model like this. But for now, let's just get to what it is. Look. Gravity model of trade is the model that tries to explain trade between two countries as a function of some normalizing constant A and real GDP product taken to the power of alpha and divided by distance between the countries to the power of beta. And look, it makes perfect sense. We don't put interpretation on the constant, we use it for estimation. But over here, GDP product. So we multiply GDP of two trading partner countries. And look, the bigger the GDP of the two countries, we expect the more they will trade with each other. And look, it makes perfect sense from both sides. Income side, the bigger the income, bigger the GDP, bigger the income, the more money we have to spend on imports. We will be importing more. And from the production side, the more we produce, the more goods we have to sell abroad. So it's as you see, it makes perfect sense. Distance. D is distance between the two countries. And look, we are dividing by D. So the bigger the distance, the lower the trade. Makes sense? Well, perfect. The bigger the distance between two countries, on average, the bigger is the trade cost, the transportation cost, and we expect lower trade. Now, what are the elasticities here? Look, again, all we need to do is to take natural logarithm ln trade, and it's equal to ln A plus alpha ln y, GDP product minus beta ln D. Okay, so again, what is the elasticity of trade with respect to GDP product? Well, it's simply equal to alpha, which means that if GDP product increases by 1%, then trade increases by alpha percent. And the same goes for beta, because beta measures elasticity of trade, negative beta, sorry, trait with respect to distance. Because if distance between two countries increases by 1%, on average we expect the trait to fall by beta percent. Again, in the second link in the description of this video, you can find actual estimates of alpha and beta for the European Union, and you can see that this model actually works very well. And using what we found over here, and the relationship that we found over here, is very important, and you will have to know it because you will have to also use it in your international economics class in the future. Okay, and the final thing for today is the relationship between growth rates and elasticities. Well, this might seem like a surprise, but I'm going to show you. But actually, you'll see that with some very basic tools we've learned today, we can get very powerful and insightful relationships between variables or of most general functions. Okay, and we're going to start with the production function. Look, what I know from this, I know that GDP is some function of capital and labor, but I don't know what type of function it is, and it doesn't really matter for me. Look, now my goal is to express growth rate of GDP in terms of growth rate of capital and labor. How can I do it? Well, as you'll see, even though we don't know very much, just looking at this expression, we will be able to learn quite a lot. But first thing we need to do with this expression is to calculate. Okay, one more thing. We are assuming that k is some function of time, L is some function of time, and consequently y is also a function of time. But besides that capital increases over time, labor increases over time, we do not know anything else. Okay, but let's go back here. So, we've got, first thing we've got to do is to calculate total differential. And again, I imagine that your memory on total differentials and total derivatives is not very fresh. So I also put links in the bottom of the description that will get you will let you speed up and learn. Refresh your memory on total derivatives and total differentials. Okay, so first I calculate total differential of this, and I get out of this that dy is equal to derivative of f with respect to k, or simply partial derivative of y with respect to k times dk, right? So if k changes by some small amount, y changes by value of this partial derivative. And the second source of change over here is dy, dl, dl, right? Because in this function we have two arguments, two things can change, and this will be influencing y. Now, thing we can do here is also to go to total derivative. So we divide both sides by dt, which is different than 0. Right? So we get that dy dt is equal to Now we made it look more complicated, but actually is this telling us anything more? There is a trick we've been all of this. Because look, we definitely want to have some growth rates here. So let's rewrite these growth rates. We know the growth rate of y is equal to dy dt divided by y. Which means that if I multiply both sides by y, then dy dt is equal to growth rate of y multiplied by y. And look, by the same token, I've got the growth rate of k is dk dt over k, which implies that dk dt is equal to rk, growth rate of k, times k. And finally, by using exactly the same reasoning, we get that dl dt over L is equal to growth rate of L, which implies that dl dt is equal to RL times L. Now, we know that we can substitute for this, and for this. So let's do so. We've got that this is Ry times y equals to dy dk times, I'm going to do it like this. I'm going to change the order. Times k times rk plus dy dl times L times L. What can I do? What else can I do? Look, I definitely don't want to have this y over here. How about I divide both sides by y? If I divide both sides by y, I'm obtaining this. And I think this should remind us something. Look, if I just will change one thing, because multiplying by k over y is the same as dividing by y over k. And the same here, dividing by y over L. What do I have? Growth rate of income is equal to partial elasticity of income with respect to capital times growth rate of capital plus elasticity of income with respect to labor times growth rate of labor. Okay, and at home, I would like you to do very similar thing that I did here. You only need to go through exactly the same steps, but we do it for money demand. So we've got money demand as a function of income and interest rate. Now, please get from this expression to this expression, and of course we are assuming that y is a function of time, and interest rate is also a function of time. Now, what is important? Please know how to do it by heart. I like to give question about it on the final or midterm. Of course, if you know how to do this, you'll know how to do this. Also know it by heart. You please know by heart how to derive a formula for the growth rate of a product, growth rate of a quotient, and growth rate of a sum that you will find, of course, that we've covered